Hello and welcome to a video on Boolean algebra. In this video we're going to look at the fundamentals of our logic operators so that we can start simplifying logic expressions. The first thing we're going to look at is the associative property, but you can think of that as how can I group these terms. If you look at addition, the expression 1 plus 2 plus 3 will give you the same answer if you do the 2 plus 3 first or the 1 plus 2 first. But if you consider subtraction, 3 minus 2 minus 1 will differ if you do the 2 minus 1 first before the 3 minus 2. That is because addition is associative while subtraction is not. So what about our Boolean operators and or? Does A and B and C still give you the same answer if you do the B and C first before the A and B? And what about A or B or C? Will that give you the same if you do the B or C before the A or B? Yes. You can prove this by building a very simple example circuit in Circuit.js, but for now you can just take my word for it. That means that there's no need to write brackets around repeated operations. So A and B and C can just be written as A and B and C without the brackets, and similarly with the ORs. Next we'll look at commutativity, or can I rearrange these? If you think of addition, 1 plus 2 is the same as 2 plus 1. This is not the case for subtraction. So our Boolean operators and or, it's pretty easy to see that A and B is the same as B and A, and similarly with the OR gates. However, it is generally expected to be written in alphabetical order to standardize the expressions. Next we'll look at distributivity, or how can I expand this? If you think of multiplication, 2 times 1 plus 3, you can expand the 2 into the 1 plus 3 to get 2 times 1 plus 2 times 3. However, 2 plus 1 times 3 does not get expanded into the brackets. This works very similarly for our and or operators. A and B or C will get expanded to A and B or A and C, while A or B and C will not get expanded. So you can just remember how it works for multiplication and apply it to our Boolean operators. Next we'll look at the basis for simplification. Since this isn't a computer science course, don't worry about memorizing these terms, and instead just look at the logic on this slide. Let's start off with the AND gate. Remember that the AND gate will only output 1 if both of the inputs are 1. If both of the inputs are x, then the AND gate will output 0 if x is 0, and 1 if x is 1. Therefore, we don't need the AND gate, and the output will be x. If one of the inputs is instead fixed to 1, then the AND gate will output 1 if x is 1, and 0 if x is 0. So again, we can replace the output with just x and skip the AND gate. If the input is instead fixed to 0, then no matter the value of x, the AND gate will always output 0 because both of the inputs are not 1. Similarly, if the inputs are x and x prime, then both of the inputs can never be 1 at the same time, and the output will remain 0. Next we'll look at the OR gate. Remember that the OR gate will output 1 if one or both of the inputs are 1. So if both of the inputs are x, the OR gate will output 0 if x is 0, and 1 if x is 1. So same with the AND gate, the OR gate can be replaced with just x. If one of the inputs is instead fixed to 1, then the OR gate will always output 1, because one of the inputs is 1. If the input is instead fixed to 0, then the output of the OR gate depends only on x, and if x is 0, the output is 0, and if x is 1, the output is 1, meaning we can skip the OR gate and make the output x. If the inputs are x and x prime, then at least one of the inputs is always 1, so the OR gate must always output 1. Using these rules, we can discover the easiest way to simplify inversion. Here I have the truth table for the function we wish to invert. Remember that inversion will simply take the original output and instead output the opposite. So we can find the truth table for the inverse function by swapping all of the bits in the output column. Now we just need to construct a logical expression that represents the truth table. And we can do that using terms. Each row of the truth table can be uniquely determined by taking the input terms and combining them with AND gates. For example, if I wanted to output 1 only when A, B, and C are 0, then the term I would use is A0, B0, and C0. This term would only output 1 when all of the inputs are low, and would output 0 otherwise. In order to construct a full function for the truth table, we can simply combine all of the terms representing the rows that output 1 with ORs. Now we just need to simplify this expression. And we can simplify by using the distribution rule. Here notice that the variables highlighted in green are shared between the two terms, and can therefore be pulled out of the OR operation like so. Also remember that B0 or B will always evaluate to be true, and therefore our expression A0, C0, and B0 or B can be simplified to A0 and C0 and 1. Also remember that if one of the inputs to an AND gate is 1, then the output will only depend on the other variable, and therefore this can also be simplified to A0 and C0. In order to continue our simplification, we're going to have to apply a rule that I found the most difficult. Remember that x or x is equal to just x, but we can also apply this in the reverse to get a duplicate term. Here I want to use it to duplicate the A0, B0, and C0 term. I want to do this because the A0, B0, and C0 term also shares variables with the A, B0, and C0 term. Therefore, we can pull out the B0 and C0 out of the OR operation and reduce the A or A0 term, just like the B0 or B term we did before, and arrive at our final simplification. In order to better explain the rules for inversion, I'm also going to pull out the C0 of the OR operation. But normally you'd use the A0 and C0 or B0 and C0 as the final answer. Looking at our question and answer side by side, I hope it will be clear what inversion does to a function. Notice that all of the terms are now inverted, and that the AND gate is now replaced with an OR, while the OR is replaced with an AND. So to invert a Boolean expression, maintain the order of operations with brackets. The AND operation is performed before the OR, so in the inverted function we put brackets around the A and B to perform the OR first. Invert the terms and swap the gates, and then you can expand at the end using distributive property. So A and B or C inverse can simplify to A and B inverse and C inverse. Notice that the inverse here is distributed, and that the OR gate is replaced with an and the C term is inverted. Then the inverse of A and B is A0 or B0. Again, the variables are inverted, and the gate is swapped. And then you can distribute the C0 into the OR, like so. Next we'll look at a more general example to simplify, but this one still includes inversion. I like to do the inversion first, and you can think of it as a simple three-step process. The first step is to distribute the inversion to the terms inside, replacing the OR gates with ANDs. The second step is to invert all of the terms, replacing the variables with the inverse and replacing the AND gates with ORs. Here, A0 is just A, while the inverse of C and D is C0 or D0. And the final step is to do any distribution. So we distribute the A into the C naught or D naught to get A and C naught or A and D naught. Now notice that our last two terms share the A and C naught variables. So therefore we can pull them out of the OR operation and simplify the B naught or B to 1. Now notice that we have a duplicate term. Remember the duplicate terms separated by an OR gate can be simplified to just the term once. And therefore, our full expression can be simplified down to A and C naught or A and D naught. So, things to take away from this presentation. Remember the order of operations when evaluating expressions. Brackets, then ands, then ors. Remember how to distribute AND over OR operations. Here the A gets distributed into the B or C as A and B or A and C. Remember the logic simplifications we covered. And practice reading terms from truth tables to create an expression. And lastly, definitely remember how to invert expressions the easy way. And that's all for this presentation. Thank you for watching and hope to see you next time.